Continuing with our discussion on vector algebra, we now look into the concept of the unit vector. A unit vector is a vector that has a magnitude of exactly 1, no unit, and points in a specific direction. That's basically the job of a unit vector. It's simply pointing in a particular direction. In terms of the Cartesian coordinates, you have the x-axis and the y-axis. And for three-dimensional vectors, you have the z-axis. You have three unit vectors: I hat, j hat, and k hat. I hat is a unit vector pointing towards positive x direction. J hat is a unit vector pointing towards positive y direction. And k hat is a unit vector pointing towards positive z direction. So you have I, j, k for the x, y, z directions. If you apply negative of a vector, negative I hat will be a unit vector pointing towards negative x direction. Diba? You'll recall, negative of a vector, same magnitude, the direction is in the opposite direction. So the direction is reversed. So instead of heading towards positive x direction, if you have negative I hat, it will be heading towards negative x direction. Negative j hat will be heading towards negative y direction. Negative k hat will be heading towards negative z direction. Unit vectors. One use of unit vectors. They are used to describe the vectors. They are used to determine the directions of the components of the vectors. So you have A is equal to AX I hat plus AY J hat plus AZ K hat, where AX is the X component of vector A, AY is the Y component of vector A, and AZ is the Z component of vector A. So this equation basically tells you A is a vector that has X component, AX, in the I hat direction, positive X direction. AY component in the J hat direction, and AZ component, Z component, in the K hat direction. And if you get a modified version of the Pythagorean theorem, A is equal to square root of AX squared plus AY squared plus AZ squared, you get the magnitude of the vector A. Performing vector addition and even subtraction with unit vectors is just a matter of adding all the x components together, adding all the y components together, adding all the z components together. Reminiscent of the y component. You'll recall in the y component, after dividing the vectors into x and y components. You add all the x components together. You add all these y components together. And extending that to the z component, you add all the z components together. So it's very easy to add vectors together if they are in the notation of unit vectors. That's because the vectors are already divided into their components. For example, consider these two vectors, vector A and vector B. Vector A is 5 meters I hat plus 2 meters j hat plus 4 meters k hat. Whereas vector B is 3 meters I hat minus 2 meters j hat plus 3 meters k hat. Let C be equal to A plus B. So plus B, so positive times B, B remains the same. So A plus B, you add all the x components together. So x component of A plus x component of B, 5 plus 3 will give you 8 meters I hat. Add all the y components together. 2 meters minus 2 meters, 0. So no y component, 0 j hat. And add all the z components together. 4 plus 3 will give you 7 meters k hat. So since 0, the y component is 0, we can exclude that in our equation. C is equal to 8 meters I hat plus 7 meters k hat. Next, we have D is equal to A minus B. So, add all the x components together, bearing in mind the minus, negative of a vector. So, 5 minus 3 meters will give you 2 meters I hat. Y component, 2 meters minus negative 2 will give you 4 meters j hat. Z component, 4 meters minus 3 meters will give you 1 meter k hat. So C, or rather D, okay, correction, this is not C, but vector D is equal to 2 meters I hat plus 4 meters j hat plus 1 meter k hat. So that's it for now. We'll continue our discussion on vector algebra in the next video, wherein we look at vector multiplication. So thank you for watching.